Welcome back again. We'd like to thank all our presenters and to our audience for tuning in. There's been a very good audience, and it's very pleasing to have put this conference on and to have this level of response. Good questions, good answers, and so we were looking forward to doing more of these in the future. Please share our YouTube channel address with your friends and post on Facebook, etc., so that we can get even more people along in future, and they can have a look at these existing stuff that will be stored there. For our final presentation, it's me again. I'm here to talk about waves of galactic clusters and the Hubble constant. We're back to the very largest scale of the universe. I won't give you all my information again because you had all that before. So I've got to work out, share my screen, yeah. Well, I'll mention this first. There regular concentrations of galaxies have been found out to a very large distances. The spacing is around 586 million light years, sorry. Assuming that this matches a geological cycle, because there are huge standing waves in space, the Hubble constant can be determined very accurately. This has been possible for several decades. That's the one. Not very good at this, as you can see. You're getting the screen share, but I haven't managed to go to full screen, have I? There we go. Sometimes it's a bit slow. It's supposed to happen when I hit F5, but it doesn't. Well, I may just have to do it like that. Oh, here we go. Finally got there. Okay. So that's me. The subject, waves as galactic clusters and the Hubble constant. So these concentrations of galaxies have been very regular ones found out at intervals of 586 million light years, very large scale. This is the largest scale structure we can see in the universe. Assuming that this matches the geological cycle of 586 million years, it means that it would indicate there were huge standing waves in space, and the Hubble constant can be determined very accurately by comparing these two things together. On the 10th of March 1990, New Scientist published a review of an article. The title was 128 megaparsecs upon H periodicity and galaxy redshift, observed by Tom Broadhurst, Richard Ellis, David Koo, and Alex Saleh in Nature, volume 343, page 726. Now, I got very excited about this because the first thing we've got to do is realize that that astronomers use some very strange units. And there's the graph itself, which I've put up here now. It's got a mistake in it because it should say megaparsecs divided by h0. Now, what is h0? h0 means that the distance depends on the actual Hubble constant. For a long time, they didn't have a clue what the Hubble constant was. The values that were estimated ranged by a factor of 2. And so they put this part in so that you could adjust for it later on when the Hubble constant got known better. And what I was trying to do then was to use this to say what the correct Hubble constant was. There are other assumptions built into this figure also. It's based on measured velocity steps of 12,800 kilometers per second between each peak. This in turn is based on the assumption that redshift is a measure of velocity. I don't think this is correct, but it does not affect our calculation. It's very clear that there are clusters of galaxies at very regular intervals. Various astronomers have suggested that this looks like some sort of wave phenomenon, which is the most reasonable conclusion. That being so, there ought to be some regular oscillation period that matches it. Now, Chuck described simple harmonic motion, and he gave the formulas for how these motions work. And it's an interesting thing because you've got the relationship is the speed of the wave in a medium is equal to the wavelength divided by the period. And when I've sometimes told this thing to astronomers, they've said, no, but you're doing numerology. And I say, what are you talking about? And they said, 586 million light years and 586 years have got nothing to do with each other, just the same number. I said, well, it has got a lot to do with it, because what is the oscillation period of a standing wave with a 586 million light year length? And they say, I don't know. I said, well, it's a simple formula. I give them the formula, and they sit there, they think about it, and after the end, they say, okay, it's not numerology. But I've been through this multiple times, so I wanted to make that very clear right from here that that it's not numerology, it's actual physics. Now, the reason physicists don't know this, because in this case, it's a very obvious matching period, and I found other cases where there's obvious matching period with the wavelengths, but astronomers use weird units that hide this fact. In popular literature, we see mention of light years, but astronomers use parsecs. 1 parsec is 3.26 light years, and the unit arises because a star with a parallax of 1 second of arc, that means the Earth's orbit extent is 1 second of arc as seen from that star. That's the distance for 1 parsec. Apparently, early astronomers thought it was better to invent a new unit than to multiply by 3.26. This is Brand of Ray's humor, a little digging humor. The result is that a number of otherwise obvious matches between cycles, periods, and distance regularities have been missed by them. So then we've got this problem with the numerology that happens. And when we get over that, we can see that this graph was first published. The Hubble constant was very uncertain, but I was able to determine that this spatial periodicity matched a period very similar to a geological cycle. Now, this time I did not know Professor Afanasiev's cycle period that I gave in my first talk. I only knew the doublings that the geologists had mentioned in the megacycles book. And so I thought the period was about 590 million light years. Subsequently, I gave my talk in Russia, and Professor Afanasiev gave me his book, and what's happening? Here we go. In his book, down the right-hand side, you'll see a whole series of figures, 586 million and various hundreds of thousands and so on. They're all very near to 586.24 million years. Now, I don't know exactly what's going on in this table. All I can see that he's made 12 different estimates, and he's averaged them out to get down the bottom, 586,238,657 years. He reckons that's within 100 years. So this is the period that when I had these figures, I got very excited, because combined with that other data of the graph as given by the astronomers, it was then possible to determine the Hubble constant very accurately. And I set about doing that. The answer I got, that was, and it's limited by the accuracy of the spacing of the galaxies, I got 71.2 plus or minus 0.3 kilometers per second per megaparsec for the Hubble constant. Now, the Hubble constant is the linkage between the red shifts of galaxies and the size of the universe, or the size of the observable universe, as believed by the Big Bang Theory. It's a link between the red shift and the distance, if you like. If the full galaxy data from the above graph, if I had that, I could make a more accurate figure than this. But anyway, in Wikipedia in 2014, when I last looked at this, there were 9 determinations since 2000 of the Hubble constant, and they spread over about a range of 10 kilometers per second, which was far less than when I first gave a figure in 1990 something. So these figures average out to 71.2. So they get exactly the same figure I got for the Hubble constant on average, but their figure wouldn't be seen to be that accurate. It's just a lucky coincidence that they are the same. There are many more estimates of the Hubble constant listed in Wikipedia today. And this is a chart that I put out. It's basically a repeat of the other one with a few quotes put on it. It says, galaxies form mega walls across space. That was the title of the article in the New Scientist magazine on 10th of March 1990, page 17. The walls seem to be spaced in a very regular way that current theories of the origin of the universe cannot explain. Now, that's a very important point, which I'm going to come back to repeatedly. I've got results from a joint US and Australian project published in Nature. Now, somewhere else I thought I saw US and English. Now, it may be there were English people working in Australia, because I thought they did the observations, one in the Northern Hemisphere and one in the Southern Hemisphere, to get this chart. So what they did is they called it a pencil beam. They looked out just a very small area of the sky, but out to an incredibly long distance, and they counted all the galaxies and they measured their red shifts to get this. And then they did the same thing in the opposite direction in the sky, and these two have been combined, and this is what you get. And you can see there's a great regularity in these peaks, and right out to the 10th one is at 1280, 1280 there, and so they're at 128 megaparsec spacings each upon H naught. Now, so two things about that. One is it gives us the spacings that we can use to compare and get the Hubble constant. But the other thing which is very important is if we look at the spacings, they are very regular at the beginning and at the end. There's no difference in the spacing. Now, if the universe was really expanding, then when we see these ones, the ones that are at 1280, that is a distance which is about a third of the way back in time to the Big Bang. So if that was true, the spacing would be smaller then by a third. But they're not closer together out there. They're equally spaced, those peaks. So we can say this thing on its own disproves the Big Bang theory. There are lots of other disproofs as well. But what this shows is that the spacing of galaxies 5 billion years ago was the same as the spacings of galaxies now. So we need that to sink in. If the spacing was the same then the universe cannot be expanding. There is a possible explanation for this, and I worked out part of this myself. I worked out from a harmonics theory that that the structure of the universe is making finer and finer details all the time. So unlike the Big Bang, where you start with the little tiny things and you build the bigger things, this happens in the opposite order. You see the space, you first of all form huge waves of the universe, form galactic clusters and galaxies, then stars, then planets, then moons, then on down to cells, atoms, and subatomic particles and quarks in that order. But that all happened a very, very long time ago. And but the process continues. And what it means is energy is always moving from the larger waves to the smaller waves. This happens because the fundamental equations of the universe are nonlinear. Now, how do I know they're nonlinear? People sometimes talk about this. I know they're nonlinear very simply because if they were linear, we wouldn't see anything. Our eyes depend on the nonlinearity to observe the light. And if you have linear equations, waves pass right through each other without any interaction. So if, for example, you drop one stone in a pond, you'll get a series of ripples going out. If two people do that at once, the ripples will crisscross each other, and they'll more or less carry on outwards without any interaction. But in actual fact, there is a tiny bit of interaction. It depends on the depth of the water, how much interaction there is. With light, it's generally considered to be linear. But for all intents and purpose, light that's travelled over large distances in space is linear. But in the presence of matter, it becomes very nonlinear because, in my view, matter is a type of standing wave of electromagnetism. So it's like light, but it's much higher frequency, and it's interacting. The interaction happens with that light, and that's why we're able to see things. So the proof that the fact that there is this nonlinearity means is what causes harmonics of waves to form, and they happen very slowly in the large-scale universe because it takes a long time for light to get everywhere, and it's at a very slow rate anyway. And in fact, the Hubble redshift arises because of the rate at which energy is being lost to harmonics. This means that two things result from this. One is that we get the redshift of galaxies as seen far away. They aren't really being redshifted. What's really happening is, as energy goes to smaller scales, the frequencies of atomic particles get faster. And when they get faster, that means when we compare the distant galaxies to the close by ones, we see that they're redder. But really what's happened is they didn't get redder as the light came. We got bluer in the meantime while they were coming. So that's an important point. Now, after I'd done this, I discovered that I wasn't the first one to come up with the idea that this was happening. It was put forward by a guy named Nodal, and it was supported by others like Sir Fred Hoyle, who was a very bright man. And so we should understand that it's not due to the motion or expansion of space, but rather to a change in particle masses over time, and it's called the variable mass hypothesis. So that's a subject for another day to go into more details, but it's a very interesting way to look at the universe differently. And once you do that, you can understand that the universe is vastly more ancient than the Big Bang theory people think, and vastly larger also. So we've got this matching up there of those two things, and we've got the estimate of the Hubble constant. So what is the Hubble constant? The Hubble constant is the rate at which energy is being lost to harmonics, and of course, and its apparent redshift. It also works out that from the same thing, if energy is being lost to harmonics, then I believe that every particle is a standing wave. And Chuck mentioned some of this about the work of de Broglie and so on. And Feynman also talked about incoming and outgoing waves from an electron. And he didn't say that was the electron, but if he'd gone that final step, he would have agreed with Milo Wolf that an electron is just a wave coming in, passing through the center and coming out again. So that gives you this picture. But if harmonics are being formed in the particle, if new structure is appearing, if energy is moving from the nucleons to quarks, if quarks are very gradually being made inside there, only one part in 14 billion per year, then what would be the consequence? It would mean that the incoming wave had lost a little energy when it came out. So the incoming and outgoing waves of a particle would have that difference as measured by the Hubble constant. If you assume that's true, then the result of that in terms of how that particle interacts with other particles is it sucks. Gravity sucks. It produces gravity. You get the correct answer for the strength of gravity from the waves coming in being slightly stronger than the ones going out, ever so slightly. The difference is only 1 part in 10 to the 40. So you couldn't measure it if you could measure those waves, which you can't. But theoretically, you can arrive at that conclusion. So I'm roaming around the subject because I've covered all that I wanted to cover there. So I'm doing stuff that's related to it. Let's see now. Let's get rid of that one. We've finished doing that. Someone asked a question, T. Pickerel. Ray, before you close, how has fractal, nonlinear, chaos theory affected or added to cycles and or harmonic theory? Okay, so there's a lot of people have studied a lot of stuff to do with fractals. Very good work by, what's his name? Mandelbrot, and it's absolutely fascinating stuff. But I'm going to argue that the universe is not fractal. The universe is nearly fractal. And why is it nearly fractal? Because these very large-scale waves are losing energy to the harmonics, and they gradually create further structure within them. So you get these levels of structure like these supergalactic clusters, and then you get galaxies, which is the first really strong structure that appears in the universe. And then at about a similar ratio from the Hubble scale to the galaxy, you get that ratio again, which is about 34,560. You get stars formed. And then when you get that interval again, you get planets. And when you get that interval again, you get moons. And when you go that interval again, there's nothing obvious, but it's about a mile. And when you go that interval again, it's about 2 inches. And when you go that interval again, it creates cells. And when you go that interval again, it creates atoms. And when you do that again, it creates subatomic particles, protons and neutrons. And when you go that interval again, you get the quarks, or as Americans say, quarks, same thing. Now, so that's what the harmonic series has happened, but those intervals are not exactly the same, each one. There's a little bit of difference because it makes many ratios of 2 and some of 3 and 5 and occasionally 7. But every so often a different number pops in. And the result of that is that at each one of these scales, there is a difference. So at many scales, like in a galaxy, we have a clump in the middle and spread out mass circling it. In the solar system, we have a clump in the middle, the sun, and the planet circling it. In atoms, we have the nucleus in the middle and electrons circling it or doing something around it. Those things are not the same. An atom doesn't look exactly like a solar system, which doesn't look exactly like a galaxy, but there's obvious similarities. They all work on an inverse square law for the attraction. Although there's some debate whether there might be a little bit of difficulty in that with galaxies. But so that's the first thing. So nonlinearity, yes, nonlinear is very important in this whole process to make this nearly fractal structure. Chaos theory got very popular for trying to explain why cycles could appear at ratios of 2 from each other, and it will do that. And so chaos theory is an interesting mathematical concept, but in my opinion, it's not what's happening in the universe. In my opinion, there's no chaos in the universe. The universe is totally driven by laws. I agree with Einstein on that. And I think Schrödinger agreed on that as well, because he didn't like some of the stuff they came out with. And his whole thing about Schrödinger's cat was actually supposed to be a way of ridiculing people, but they never caught on to that, and they've continued to make that in a serious thing. So chaos will do those times 2s, but it will not do a thing that goes like what we actually observe with the common cycles, that we find a cycle that's times 2, then times 3, then times 2 and times 2. It won't produce that at all. It can produce either all times 2s or all times 3s. So I think I can prove that chaos theory does not explain the observed pattern of cycles that we see. So that's a very good question. And it's an area which I need to engage with first of all, I've got to get some of these physicists and cosmologists and so on to start looking at what I've done seriously with harmonics theory. And then it's possible to start to debate these things and show that what I've done will explain the things better than what they've done. The Big Bang theory originally was created to explain one thing, which was the redshift variation of galaxies with distance. And it did that fine. It predicted there would be a cosmic microwave background, although the original answer was out by a factor of about 20 at a time when Eddington could get the correct answer by a different assumption, by the starlight eventually becoming thermalized. So, but since then, just about every time they discover something new, the Big Bang has had to invent some new thing, some new type of invisible things and some new processes or some rapid inflation for which there's no evidence in any of the equations of physics that should happen. It's just like, and a Fury waved a magic wand and this happened. That's all they're really saying. We shouldn't need to do that sort of thing in science. And there's been people who have shown that the Big Bang really doesn't produce all the results. And they can produce one at a time when they vary the parameters, but not all of them at once. Okay, enough of my rant against the Big Bang. Harmonics theory agrees very well. It doesn't have any arguments with general relativity or with quantum mechanics. I think we can add a little bit of stuff to quantum mechanics to make it clearer, to understand what particles are. And I would recommend people to read the works of Milo Wolf, who talked about the wave structure of matter. When I first put my own ideas on the internet about the wave structure of matter, I got an email from Milo Wolf and it said, "Welcome to the club." I said, "How many are in the club?" He said, "2 now," which I really thoroughly enjoyed. But over the next few years, quite a few more joined, and there were quite a few other people arguing that atomic particles were standing waves, energy coming in waves to a center and going out. In fact, this was preceded by several other people before us. Feynman and Wheeler almost got to this when they described how an electron, the waves of an electron happened, that there was, they called it a wave going out in forwards in time and a wave going outwards backwards in time. Now, I would call a wave going out backwards in time as a wave arriving forwards in time. It's much easier, but I don't think they could work out how to explain that it all arrived there. And the answer is it didn't have to know where to arrive. It happened that it was all arriving. It happened that a wave was converging, and where it converged, that is where the electron is, and then it goes out again. And so this is the way to get rid of the duality that Chuck talked eloquently about, all the different reasons for it, the duality of particles and waves, because we have a wave coming in. It has a particular frequency. It's called the Compton frequency of the particle. You can determine it exactly from the mass of the particle, what that frequency is. And then as the wave passes through the center, it comes back out again. And that is what the particle is. That is what an electron is. Protons and neutrons are a bit more complicated, and I don't know the exact arrangement for those. But Milo Wolf has proved that that arrangement for the electron will satisfy all the known properties of the electron. So I would recommend looking up wave structure of matter and Milo Wolf. I would also recommend looking at Gabriel Lafreniere. Now, he died a few years ago and his site disappeared, but a lot of it's been copied to a couple of other sites, so you should still find them. He made some wonderful animations showing what happens when these particles come in and when these waves come in and produce particles. And he showed how a particle in motion, the wave was converging on a point that's moving in space. And he showed how the incoming wave and outgoing wave interacted to make the waves exactly as de Broglie described them. But when de Broglie describes them, they sound very mysterious. But when you see these animations, they're no longer mysterious. This is a way to demystify physics. And as we see more and more of these things, we start to go, so that's what that means. One of the ones Chuck mentioned, he didn't always agree with me, and we've had some interesting, I have to say, I agree with 99% of what Chuck says, and he possibly agrees with as much as 90% of mine, I don't know. But I mentioned about some Russian work which had found cycles in the rate of radioactive decay. And they had found a daily, a monthly, and an annual cycle. And I said, could I have some of your data, please? Because I think there could be 3- and 6-minute cycles as well. And they sent me a month's data and I analyzed them. And there were very clear 3- and 6-minute cycles in them. Now, why did I think those periods exist? It's because the inner solar system, the inner planets are arranged at more or less regular spacings of 3 light minutes apart. The outer planets are arranged at spacings of about 80 light minutes apart. And these 3- and 6-minute and 80 and 160-minute cycles are found all over the place. They pervade the universe. So I believe that they ought to have an effect on radioactive decay, because they, in my view, a particle sitting there and it's on the brink of collapsing. You know, a uranium atom it's sitting there, it's wobbling about, nearly collapsing, and if it gets hit by the right stuff at the right time, bang, it suddenly disintegrates. The conditions for that are very critical, because it takes a long time. The half-life of the uranium is very, very long. But when the Russians sent me that, I analysed the data they gave me for about a month, and I found 3 and 6 minute cycles. And they said, well, we didn't find those. And I said, that's because you were not analysing it the same way as me. And I described the way I did it. It's what I call a voice print, where we put time along here, and we put frequency up this way, and we show how strong the vibrations are there. And this is often used to show, it's not really called a voice print, that's just my name for it. It shows the various different vibrations in many different things, how they vary over time. And when I did this, I got very clear 3 and 6 minute cycles. Shortly after that, I was going to Russia, and Dr. Udaltsova had gone through all 18 years of their data of 1 minute measurements. I had 1 month, and she showed me the graphs, and all through it were these 2 horizontal lines at 3 and 6 minutes right through the whole thing. So I regarded that as proven that 3 and 6 minute standing waves in the universe are influencing slightly the radioactive decay of plutonium. Now, Chuck didn't agree with that, and he even went so far as to try and do some experiments on this, but he reckoned there was problems with the timing. And I think he's got a blind spot there. So I'm looking forward to debating that with him more. But what happened is subsequently, that some Western reports happened that they had found a 1 year fluctuation in the decay rate of a number of different radioactive substances. And these different ones, they attributed it to the distance of the Earth from the sun. And I think that's probably a very good conclusion to come to, because the Earth's in this elliptical orbit. We're sometimes close to the sun, sometimes further away. And I think it does relate to something like gravitational potential. And so these waves that I'm describing of the inner solar system through the planets, and these the gravitational potential changing as we get nearer and further to the sun, these things are all working together. And I think those things also will ultimately lead to understanding the LA effect that was mentioned by Pavel in his talk, where it's been found that when there's an eclipse, and when there's a solar eclipse, that strange things happen to gravitational things like pendulums and so on. So science isn't finished; it carries on. And some of us that some of the scientists will regard as a loony fringe are actually the ones that first of all start to discover things, and then and I might add, I might put David in that category. I was a little bit harsh on him at the end of his talk, but it's people thinking about these things which are more esoteric, who and then later on other people start to do that, and they do some science on it, and they find, oh, it's not that far out, it's something like that. So this is how science progresses. You have to have people that are thinking up ideas and trying them out, and other people that are testing them out. And then eventually what they discovered in the times of quantum mechanics in the 30s and so on is you don't convince other people of them. What happens is you start teaching it to the young people, and eventually the old ones die off, and that's how new knowledge gets into the world. Right, what else have I got here? No more questions coming through. Mark, I can't believe there's no one got any questions. Yeah. Yeah, yeah, sure. Yeah, yeah. So yes, well, for that, the first place I'd recommend people to start would be Edward Dewey's paper, The Case for Cycles. If you search The Case for Cycles, Edward Dewey, on Cycles Research Institute site, you will find this paper. And he goes through it and he describes how there are cycles are found in things, how there are certain periods that pop up multiple different times in different things that seem to be unrelated. And then he shows how the ones that have the same cycle period often have synchrony. They all have their peaks and troughs together. And then he shows that a number of these different cycles periods are harmonically related. He has a 17.75 year period. He shows there's an 8.88, half of that 4.44, half of that 2.22, and he doubles those, and he also divides them by 3 and multiplies them by 3. And a lot of these other ones turn up. And I extended his chart by doing a multiple of 5 above that and a division of 7 below. And that included several of the other cycles that he had found that he didn't have listed in his original chart. So I believe that's fairly well established, that whole thing. I do have a graphic somewhere which has got all the cycles, the main cycles from 586 million years down to about a month or a week. So beyond that, I know there are more, but I haven't got the linkages. I cannot link the cycles in the range of a week down to the 160 day and 80 day and so on. So that's, and there are more groups of them further down. I mean, there's all the ones in the subatomic realm. There is a pattern in the masses, and a mass in the subatomic realm is the same as frequency. A famous Nobel Prize winner from Texas, I'm trying to remember his name, he said there are the 3 most fundamental things we've managed to come to are mass, energy, and frequency. And he says, if I had to pick which one I thought was the most fundamental, he would say it's frequency. So he was in fact advocating the study of cycles because it's the makeup of everything, cycles. So if you've got thoughts on these things, post us a message, join the foundation, get involved in these things. We will be presenting more information. I've got a series of talks, more than 20 of which are prepared, and there's about 50 in the series, which will include a whole description of the harmonics theory and other things that we've mentioned here in much greater detail. So I was going fast through some of that. I was trying to give you a flavour of all the stuff that we've got. Yeah, hope you will enjoy that. I think we could close now. Thanks.